Okay, this video is going to talk about how you calculate the freezing point depression and the boiling point elevation of solutions. Because when you have a solution, the properties of the solution are not the same as just the pure solvent. I have my two formulas here. They look kind of like ugly little things, but they're not so bad. This is a Greek symbol. I'll put it here on the bottom. Delta stands for change in. So that would read the change in temperature. The F means freezing. So the change in the freezing temperature is equal to the Kf. Well, K is a constant, and the F again is freezing. So this is really called the freezing point depression constant. That's a lot. All it really means is that it's a number that's going to be given to me. And that's nice because I don't have to memorize them. They just need to be told to me, either in the problem or in a chart somewhere. This looks like a familiar symbol to me. It is the mole, not the mole fraction, but the molality. We calculated molality in another video where it was the number of moles of solute divided by the kilograms of solvent. You can go back to that video if you need to. You can also use the power of video with this one and pause and replay as much as you need. The change in the boiling temperature is basically the same equation. There's another constant, there's a boiling point elevation constant, and it's also times the molality. The bottom line with both of these K values is that the K values are given in degrees Celsius per mole. And what that means is that there's some number here. If I have a solution, it's telling me how much the temperature will change for every 1 mole solution that I have that goes with it. So this number is just dependent upon what my solvent is. We're going to try a couple and we'll see how it goes as we progress. The first one says, what is the freezing point depression of an aqueous solution of 10 grams of glucose in 50 grams of water? Well, if it's asking me about freezing point, that means I need the equations that have the F's in them. So that's going to be delta T sub F is equal to K sub F times molality. Well, if they want how much the freezing point changes, then that means I'm looking for this that I'll underline in orange. Well, if I'm looking for that, I have to have the other two things. Well, me, the teacher, I'm supplying you with this information. I'm telling you that the Kf of water is 1.86 degrees Celsius per mole. You're just going to have to trust me on that one because it's given to you. I might even put it over here in parentheses if this was a test. So I have that part, 1.86 degrees Celsius per mole. Well, that means I'm missing this piece. I'm missing the molality. Well, I already know how to calculate the molality. It's the number of moles of solute over kilograms of solvent. Well, it's a glucose in water solution. So glucose is going to be my solute, but I don't have it in moles. So there's lots of work for this problem. I'm going to have to convert grams to moles. And if I do a little quick thinking here with the calculator's help, I will have 72 for the carbon, 12 plus 6 times 16. The molar mass of glucose is 180.0 grams. So 10 divided by that comes out to be 0.05 repeating moles. Well, then I need to take that number, the 0.055 repeating, and divide it by the number of kilograms of water. I don't have kilograms, I have grams. So I'm going to have to divide 50 by 1,000. So that's going to be 0.05. And I will get a molality of 1.11 repeating for my molality. So I'm going to bring that number over here. The most ideal situation would be don't round here, don't round there. Just carry that whole number over into your calculator to get the best possible answer. So I need to take the molality and multiply it by 1.86. And I will get an answer of 2.06 repeating. And there's a lot of math going on here, but it all comes back to I used this number originally with 3 sig figs and this number with 3 sig figs. So I can have 3, so 0.207. Now, in my problem, molality cancels, which leaves me with degrees Celsius. So my change in temperature will be a total of 2.07 degrees Celsius. Now, my next problem is a little different for a couple of different reasons. First, it asks for the boiling point of a solution. It doesn't ask me for the change in boiling point. It asks me for the boiling point. So I'm going to actually have to do the rest of the math. The one up above asked me for the freezing point depression, just how much it changed. So I can leave it like this. If it had asked me for the freezing point of water, I would actually have to do 0 degrees Celsius minus this in order to find it. This one asks for the boiling point, and it's a solution that's in water. Well, you should know that the normal boiling point is 100 degrees Celsius. So we're going to have to figure out how that changes above and beyond that. So this time I'm doing delta T sub B is equal to KB times molality. Well, KB, and you're going to take me on my word at this, it's in the problem down here below if you can see it. It's for water. The KB is 0.52 degrees Celsius per mole. Well, I need the molality. This one's slightly easier. It gives me moles and it gives me grams. So this is going to be 1.25 moles of CaCl2 in 1.4 kilograms of water, but not so fast. Whenever you put CaCl2 in water, it breaks up and makes a calcium ion and 2 chlorine ions. That's just as good as making 3 moles instead of 1 mole. So I'm going to take this number and I'm going to multiply it by 3. Because it won't be 1.25 moles of CaCl2. It'll be 1.25 moles of Ca2 pluses and 1.25 moles of 1Cl minus and another 1.25 moles of the other Cl minus. There'll be a total of 3 times that. I'm going to divide that by 1.4 and I will get a molality of 2.67 and then some other digits. I'm going to put that whole number over here. And you can look at my calculator and see, like, I just don't erase that number. I leave it in my calculator. And the very next thing that I'm going to do on paper, it says is multiply it by 0.52. So I will get 1.39 and then some. Well, this is a constant. It has an infinite number of sig figs. I'm going to have to go back to this. This has 3 sig figs and this has 2. So I'm going to have to round the 1.39 to 2 sig figs, which means the change is going to be a change of 1.4 degrees Celsius. If I ask you to find the change in, that would be your answer. But I asked for the boiling point. If the original boiling point is 100 degrees Celsius, then you're going to have to add the 1.4 and give me an answer of 101.4 degrees Celsius. If this is for us for test purposes, you would get lots of credit for getting to this point, but you would end up losing a point for not going the rest of the distance and giving me the new boiling point. I may add some more problems later with how things break up. If this did not break up and it stayed together, I wouldn't have multiplied it. For example, up here with the glucose, if you notice, I didn't multiply the molarity or the number of moles by any factor because it's covalent. It stays together in solution. It doesn't break up, so therefore there's no need for me to split it apart into ions.